speaker, the last speaker of the day is, let's see, Andrew Conrad. And I have here.
Andrew, if you like, you can unmute yourself.
Yeah, please unmute.
And I'm sure you can share now, but you haven't unmuted yourself yet.
Andrew
Okay.
Conrad is an electrical engineering PhD student at the University of Illinois, Urbana-Champaign. Yeah.
We're leaving.
You're leaving.
Before we leave, I want to sit here to take a picture from the class, and then we leave, and then you continue.
Yeah.
Okay, can you take a picture? First, somebody want to do this?
Sounds good. Can you hear me okay?
Yeah.
Okay.
Yeah.
Okay. Sounds good. Am I good to get started?
1 second.
Okay, yeah, no worries.
Okay, thank you.
So yeah, Dr. Clauser is leaving because we have to go to the airport. So thank you very much, everyone. Good luck out here.
Thank you. Okay, Andrew is an electrical engineering PhD student at University of Illinois, Urbana-Champaign, under the supervision of Professor Paul Kwiat. He's a National Defense Science and Engineering Graduate Fellow, and his interests are drone and vehicle-based quantum communication, including quantum key distribution, entanglement distribution, quantum position verification, and remote quantum sensing. And he's going to tell us about his work on vehicle-to-vehicle quantum key distribution. Please go ahead.
Cool. Thank you. Yeah, thank you, Farbad, and thank you, Marco, for organizing this workshop and for inviting me. So yeah, I'm going to talk to you about vehicle-to-vehicle quantum key distribution. So I'll provide some brief motivation. Why could someone be interested in this? So in the US, about 1% of the entire population, unfortunately, will likely die in a car accident over their lifetime. But I'm an engineer and I'm pretty optimistic, and I think that we can try to solve that using technology. So there's a lot of car companies out there that are currently pursuing self-driving and autonomous vehicles. This is an example of Tesla. And there's a RAND study that estimates that if we deploy self-driving technology right now, like across the board for every vehicle, that it would likely save estimated hundreds of thousands of lives. Well, one drawback of current technology is that they kind of don't interact with other vehicles or infrastructure. So this Tesla car is sensing its environment and making decisions locally, but it's not sharing what it's doing to nearby cars or to traffic lights. But according to the US Department of Transportation, about 79% of all vehicle accidents in the US could be eliminated with the application of what's referred to as vehicle-to-vehicle communication. So this talk, I'm going to be presenting our work on securing vehicle-to-vehicle communication using quantum key distribution. So I'll give a brief background of QKD, although John in his talk discussed it already. But the idea is that QKD was introduced by Charles Bennett and Gilles Bessard in 1984, and it leverages an important theorem of quantum mechanics that you can't make a copy of an unknown quantum state. So this is referred to as the no cloning theorem. And the idea is that Alice is at the sender, and she wants to securely transmit a secret key to Bob through this channel, which may be insecure. And so to do that, she encodes information into the polarization of single photons. So either vertical, horizontal, diagonal, or anti-diagonal. And then she transmits those through the channel. Bob will perform a measurement, either measuring in the HV basis or in the DA basis. And then after this protocol is done, Alice will reveal what her basis choices were for each photon that was sent. And Bob will reveal which bases he measured in, but not what the result is. And Alice will not mention what the result is either. And if their bases agree, such as this green check bar, they'll keep it. But if they disagree, then they'll discard it. And if you notice, in an ideal QKD system, when the bases agree, no matter what the sending state was sent by Alice, Bob will correctly decode that same state. But in the case where the bases disagree, that messes up the state. So where does this fit in within the realm of vehicle-based communication? Well, there's really three different link types that you can look at. So this is infrastructure to infrastructure. You can kind of think of this as traffic lights talking to other traffic lights. And then there's vehicle to infrastructure, also denoted infrastructure to vehicle, where traffic lights can talk to cars. And finally, you've got vehicle to vehicle communication over here, where individual cars are talking to other cars. So if you look at prior work, there's one group out of the UK that had a free space QKD link between traffic lights. Essentially, they're denoting it infrastructure to infrastructure. And then Thomas Yenevine's group did a stationary to moving vehicle QKD demonstration previously. And his goal wasn't really to get this to work with vehicles. They were trying to test a satellite-based QKD link. But nevertheless, it still was the first infrastructure to vehicle quantum demonstration. And they achieved about 40 bits per second of asymptotic key rate. So again, we're focusing on the vehicle-to-vehicle quantum communication, which there's, to our knowledge, not been anyone that has demonstrated a vehicle-to-vehicle quantum link yet. But as you can see, we've got this difficulty scale down here, and I'm proposing that it is easy on the left and hard on the right. And why is that? Well, there's a lot of challenges for vehicle-to-vehicle QKD. So for instance, the quantum link has to go through free space, and these vehicles are in motion. So that requires active pointing and stabilization and tracking. Additionally, these cars will only have a finite size payload that they can carry. So you're intrinsically limited on the size, weight, and power of what your quantum transmitter and quantum receiver can be. Also, another problem is in the real world that they have to operate over wide temperature and vibration environments. And then even if you can overcome all of those challenges, you only, in practice, have a limited window to actually perform the QKD link. And what this means is that overcoming finite key effects, which is an important parameter for QKD, is challenging. So I'll talk to you about our approach on how we tackle these problems. So we'll go through the system. So this is kind of an overview of what our system looks like. So this is a modular QKD transmitter and receiver platform. This is kind of a cool GIF that's spinning around. So on the transmitter, we use a decoy state QKD source that's driven by resonant cavity LEDs and an FPGA and custom optics benches. And then on the receiver, we have single photon detectors and a qubit-based time synchronization algorithm. And we save all the data onto an SD card of an FPGA. And of course, both the transmitter and the receiver have to have an active pointing, acquisition, and tracking system. But one of the design principles we opted for is this so-called modular design. And in the field of quantum engineering, I would very much encourage other engineers to pursue this. And the idea is if you can make something that can be dropped into numerous different platforms or numerous different vehicles, that has a much broader appeal than if it only works with a particular platform or vehicle. So that's kind of the overview of the system. So what does our source look like? So for the source, we have research collaborators at The Ohio State University that put together this source. And we have three different LEDs. These are resonant cavity LEDs. And we're encoding information in the polarization of the single photons. So our signal bases are right and left circular, and then the error checking is horizontal. So this is a this is a decoy state. So we have a signal plus two different decoy intensities. And because we have three different sources three different LED sources to produce each one of these states, we have to ensure that in all other degrees of freedom, they're perfectly indistinguishable. So if you look at the spectrum, so they're more or less right on top of each other. We provide this using a very narrow band filter. And then we also adjust the timing of our FPGA such that the pulse emission time is indistinguishable from all of our signals and all of our decoys. And finally, we put each one of these states through a single mode fiber to ensure that they are spatially overlapped. So here's kind of an overview of what our optics looks like for our transmitter and our receiver. And so this source that I was referring to is really kind of over here on the left side. So it's producing left and right circular and horizontal. And then we use beam splitters to ensure that they are all overlapped in the same spatial mode. And we have a single mode fiber that comes over here that launches the system. Now, the spatial fiber is nice, but a huge downside is if you have a known polarization state that goes into a fiber, the polarization that you get when it exits the fiber is randomized, or it's been rotated by some unitary transformation. So to undo that unitary transformation, we have to apply polarization compensation in the form of quarter and half wave plates. So this is our source over here, and then it goes through a pointing acquisition and tracking stage on both, and then it comes over here to our receiver. And we have a 50-50 beam splitter, which separates the path and to be measured into right, left, or HV. And then we couple it into a large 1-inch collimator that goes to multi-mode fiber. So based on looking which output port the photon came from, that tells us what the polarization projection was. So let's talk about the pointing acquisition and tracking system. To do this, we have two control loops. We have a gimbal control loop and a fast steering control loop. The gimbal control loop, essentially, we use a commercial gimbal. It's denoted Movi Pro. It's typically used for filming a lot of Hollywood films. And we have near IR beacons right here and near IR cameras that it's looking off into space and it's seeing where is the infrared beacon coming from. And then it provides a control signal to move the gimbal to look in the correct direction. Now the gimbal jitter is right around 0.02 degrees, and our tracking performance is very close to these limits. So we're squeezing as much performance as we can out of the gimbal, but that only gets us so far. To get better improvement, we use a fast steering mirror. And we have, essentially, there's our transmitter over here and our receiver over here, and we have counter-propagating laser beams that go through the channel. And then we use a position-sensitive detector to measure the incoming angle of arrival. And then that generates an air signal to adjust these fast steering mirrors. So these are single-axis fast steering mirrors. So we require two fast steering mirrors in order to get tip and tilt corrections. And with these, we get around 21 and 22 microradians of pointing air at the 1 sigma level with these inner loops. And if anyone's interested, we use the LR17 fast steering mirrors to provide these corrections. And to give you kind of some other specs about the time, we essentially are sampling this near IR camera at 100 frames per second approximately, and we're sending correction signals at 50 frames per second, which is the max update rate of our gimbal. Whereas we're sampling the PSD over here around 800 samples per second, and then we're providing corrections also at 800 samples per second to our fast steering mirrors. Okay, so what does this look like on our payloads? So these near IR beacons and the near IR cameras are right on this front plate that's designed to just get bolted onto our payloads. And they're both at 850 nanometers. And then for the inner loop, we essentially have counter-propagating beams. So we have a green beam at 520 and then a red beam at 705. And the idea is this green beam exits out and we mix it in using dichroic mirrors. It bounces off the fast steering mirrors, goes through the channel, and then it's picked off by a dichroic mirror and then focused onto the PSD right here. And then based on its position here, these mirrors will update to keep it centered. And the exact same story for the 705 beacon. Okay, so what does it look like when we actually put up our full system and put everything in the cars? So essentially, this is our transmitter over here, which is denoted Alice, and this is our receiver over here, Bob. And they basically are just in the back seat, taking up the space of a human, is what the size is. And so you can see our gimbals on top, and our optics payload that I was showing you is inside this gimbal. And then all of our supporting equipment is in this equipment tray down here. At the very bottom, we've got these two wooden plates with vibration isolators in between. And then we also put some foam underneath, like in between the car seat and this wooden platform. And then we literally just roll down the window and shoot the quantum channel out from one car to the other. So this is essentially what our setup looks like. All right, so what are some of the results? So in our lab, we try to take baby steps. We start small and then we incrementally increase. So we started at very slow speeds of 5 miles an hour. And we're very fortunate at the University of Illinois. We have the Illinois Center for Transportation, and we told them about our project, and they were very excited. And they gave us access to a closed test track on the university's property. So this was conducted in coordination with the Illinois Center for Transportation on this closed test track. And the distance is not far. It's like around 200 meters is what this length is here. And for these tests, we used both our gimbal and fast steering mirrors while the cars were in motion. So the first thing we need to do is see, well, how's our system performing when the cars are not in motion? And this is essentially what our quantum channel transmission is as a function of time. So these are our individual outputs channels. So we have right, left, horizontal, and vertical polarizations. And you'll notice that all of our transmissions drop off to 0 at periodic increments. And we use those for aiding in performing our post-processing time synchronization. So when the cars are not moving, this is what the channel looks like. So this is a very nice, clean signal, more or less. So then to do these tests, we started with both cars stationary, and then we traveled with cars just parallel, moving next to each other at a speed of 5 miles an hour. And then we stopped, and then we measured what the transmission was afterwards. And as you can see, it's kind of hard to tell the difference between when we're moving and when we're stationary, which is fantastic. That means the pointing acquisition and tracking system is doing its job, more or less. So now that it's working at like 5 miles an hour, we try to crank up the intensity a little bit. And we actually coordinated with the Illinois Center for Transportation as well as the Rantoul Police Department. So Rantoul is a city just north of Urbana-Champaign. And the police provided these barricades and provided us authority to actually shut this road down. It wasn't a big ask because over here is literally an abandoned warehouse that is part of this Illinois Center for Transportation. So really no one's even using this road. But this road was around 622 meters long, approximately 3 times longer than our current closed test track, which was just up here. So again, for this, we measured the stationary signal, and this is very clean, as we would expect. And then when the car is in motion, so we started stationary and then we moved around 10 to 15 miles per hour, and then we stopped and we had stationary results over here. And as you can tell, we're starting to stress the system, at least in this current implementation. The transmission is dropping, and the average transmission is a lot less than when it's stationary. But nevertheless, we're still able to get a pretty reasonable signal through, and you can still identify the blips, which are used for time synchronization. So again, okay, so we've got to work in at 5 miles an hour, we're going to work it for 10 to 15 miles an hour. So let's crank it up to 70 miles an hour. So for this, we had to take very special precautions. Number one, we had to change our beacon. So we were using 520 and 705 nanometers, but obviously we cannot be driving on the highway shooting lasers out the window. That's unacceptable. So we had to update it to one of the beacons is now 850 nanometers, which is invisible to humans. We only had one of those. So for this test, we basically had 3 out of our 4 control loops. But we also did a safety review to make sure that the light that was emitted at 850 nanometers was within laser safety ranges for humans. So they were eye safe. And so basically the idea is we would get on the highway and, oh yeah, I should mention we're in the state of Illinois, and this is Urbana-Champaign right here. So basically southwest, we got on the highway. This is Interstate Highway I-57. And then we went south. It was about 9 miles essentially where this run that we would do. And then we would finish, get off, and then come back the other way. So this is more or less our setup. And so again, we characterized the performance just standing still, and we got very similar results. One of our channels, H, was a bit choppier than normal, and we suspect it was due to the alignment of that particular channel. So that wasn't the best data, but we had fairly clean signals on 3 of them, and we were still able to get signal through on H. Okay, so what does our actual transmission look like at 70 miles an hour? So this is what it is. Obviously, it's for sure not as clean as the stationary data or the 5 miles an hour or the 10 to 15 mile an hour, but nevertheless, we're still able to get throughput through the channel at 70 miles an hour. You can see over here, it briefly dropped out, but our point acquisition tracking system automatically reacquired. And we're just trying to pump as much much raw key through the channel as possible within as much time as we can before we have to get off the highway and then turn back around. So yeah, this is kind of a cool photo of what it looks like in our setup. So again, this is our transmitter, this is our receiver. This is actually me driving the car. This was a cool time lapse so you can see these streams are cars passing by in the opposite direction. And then we tried to essentially just match the speeds so they were both going exactly 70 miles an hour right across the window to essentially do the link. So here's the transmitter, and then the receiver is here. It's kind of, you can see this like a bit of a purple glow. That's actually from the outer loop beacon for our gimbal. Okay, so we got all this data. This is great. So now the next thing we need to do is we need to perform finite key analysis. So in the world of QKD, finite key is a process that you do to figure out, of all the key that you got, how much of that is actually secure. And it takes into account that you have limited statistics of the data. And so this is more or less very pessimistic. And it's saying, like, given the finite data that you have, you're guaranteed to have, so much is actually secure. And to do that, we partnered with Norbert Lukenhaus's group at the University of Waterloo, in particular, their PhD candidate, Lars Kamen. And we also, so basically, in collaborating with them, we put together a finite key model that took into account device imperfections of our system, for including our transmitter and receiver. And essentially, this is what our summary table is. So our 5 mile an hour, we collected data for around 86 seconds. And then the highway was around 209 seconds. Our QBER, this is our quantum bit error rate. Ideally, you want this to be as close to 0 as possible, but no system ever achieves that. The critical number is that these have to be less than 11% for the BB84 protocol in order to be secure. But what it turns out, the higher these numbers are, that just kills your finite key rate. So a raw key rate, which is just after, like, how many qubits are we able to transmit per second, is around 231 kilobits per second at 5 miles an hour, and around 45 kilobits per second at 70 miles an hour. And then our final secure key rate, we're extraordinarily happy that we were able to get a finite key that's greater than 0. Is 14.8 kilobits per second on the closed test track, and then 2.4 kilobits per second on the highway. So in summary, we demonstrated a vehicle-to-vehicle QKD link between two cars in motion. We did it at 5 miles an hour as well as 70 miles an hour, achieving raw key rates of 231 kilobits per second and 45 kilobits per second, and then secure finite key rates of 14.8 kilobits per second at 5 miles an hour, and then 2.4 kilobits per second on the highway. And to our knowledge, we believe this is the first known vehicle-to-vehicle QKD link of any kind in the world, as well as the first vehicle-to-vehicle QKD link that's been demonstrated on a public highway. And we were extremely happy that we were able to get a system and operational on the highway and actually get a finite key out on the other side. So like I said, I work in Professor Paul Kwiat's lab at the University of Illinois. Again, our collaborators are Dan Gauthier at OSU. And this is the team that we have. This is Samantha Isaac, Tamir Jarvid, Roddy Cochran, Daniel Rosales, myself, and this is our fun stormtrooper who's just, we keep him around.
Graduate.
A silly mascot. So anyways, yeah, we like to thank our funding sponsors, and yeah, I'll open it up for any questions.
Thank you. Okay, so we have questions. Yes, go ahead. Come here.
First of all, thank you for the talk. That was great. That was super interesting. I was curious about your thoughts on like future scalability, because obviously like one vehicle to one vehicle is like, you know, it's like I mean, you got to start somewhere, right? But I'm curious on your thoughts of like, you know, in the future, if you want to do this, you need a vehicle communicating both with infrastructure and multiple vehicles at the same time. And, you know, in terms of both like the laser safety constraints and also like you can't necessarily have 10 gimbals on a car that are all pointing to other cars and acquiring in real time. So I guess, what do you see as the paths forward for making this like a reality?
Yeah, no, that's a great question. And I'll go back and I'll bolster your argument or your question. And that fundamentally it's that, you know, these like this is very large, very bulky. It takes up a whole seat. It's not very practical for wide scale implementation. And so part of it is we're doing this, number one, because we're just trying to do an initial hero demonstration to show that it is possible and that it can be done more or less. As well as we think that QKD is useful for both securing the communication of vehicle to vehicle as well as vehicle to infrastructure, but also having a quantum link with a car allows that car to be connected to what will be the future global internet. And that opens up new applications such as securing someone's position or what's called quantum position verification. So I guess we see that it has multiple applications, but as far as scalability, for sure, this would have to be miniaturized and more or less put on the roof of a car. That would have to have 360-degree view so it could link up with other cars as well as passing by with other infrastructure. We haven't done the full study of figuring out what this looks like in the future for wide-scale implementation, but I suspect that trying to integrate a quantum communication layer with existing sensors such as car-based LiDAR, like trying to integrate those two together on different wavelength bands is likely going to be how it would be implemented wide scale in the future if this is, you know, if this gets implemented at all.
Thank you.
Yeah, great question.
Another question?
Marco, can you hear us?
Yes.
This is Farbot. We are driving with Dr. Clauser, but Dr. Clauser always, keep asking me when I was trying to explain this technology. The main question is, why are you doing this? And I was trying to explain about communication, security. But so if you're doing vehicle to vehicle, why don't you just do
just go from one vehicle to the other vehicle and hand them a travel drive? Or why are you worried about quantum encryption for what's the matter with plain normal encryption to talk to them if that's all that's required?
Yeah, no, I agree, John. It's a really great question. I mean, fundamentally, we're looking at this for multiple reasons, and like if you have two vehicles traveling in parallel on a highway, the likelihood that there's going to be an eavesdropper in the middle that can in any way intercept and manipulate the signals is very low. But however, as we push more and more traffic control to like autonomous vehicles, and in the future, in the limit, if every vehicle out there is being driven with autonomous algorithms and they are talking to each other, we definitely want to make sure that's secure. Now, can that be done with classical encryption? Perhaps, but quantum communication or quantum computers, are threatening whether or not public key encryption will be safe in the future. Now, potential quantum computer attacks of RF-based links for vehicle-to-vehicle, communication, that's a bit of a far stretch. So I'm not entirely convinced that we absolutely need vehicle-to-vehicle QKD necessarily. I'm more optimistic that we can use quantum communication links with robots, such as drones and such as vehicles, to do just extend a future global quantum internet to people while they're in the car on the go. And I'm highly interested in trying to use quantum links to do quantum position verification, which more or less is if someone is able to prove that they are located at a certain place at a certain time. And I think there's a lot of applications for that for future autonomous vehicles.
Does that answer John's question?
Well, I'm not so sure. I'm not convinced, but that's all right.
No, fair enough. Fair enough.
Andrew, please try to convince us. You're very clever. So I couldn't do it, but I'm sure you can do it. You can do a better job.
He's
Go
also
ahead.
driving.
Try,
He's driving.
try harder. Okay? Try
Yeah.
harder.
Yeah, no. So I mean, we've used these systems to do drone to drone QKD, and then we basically made the system modular, and we just said, well, can we put it in a car? So we did drone to drone, and then we did drone to car, and then if we put one in a car, we could easily put the other one in a car. So part of us doing this was practical motivations. We could do something. Now, again, that's not always a great argument for why you should do something, but I do think having
that was sort of my question. Yes.
yeah, for sure. And part of it is, why are we building a global quantum internet? Why is that useful? And whatever argument you can construct for having a global quantum internet could be easily extended for why one may want to have a global quantum internet that's wireless. So I guess I would say whatever argument one would have of why we would need a global quantum internet, it seems like we would also need to have that, or those arguments would extend for wireless cases. Much as we've all come to rely on cell phones being ubiquitous communication devices that we take wherever we go, whereas we just had landlines.
Can you also explain about the line of sight for quantum key distribution, the application of drone for line of sight? Can you explain that, please?
Yeah, so for line of sight, so basically QKD requires an optical line of sight. So the way this works is we're literally shooting single photons from one platform to the other platform. And for the most part, single photons go in the direction that you shoot, notwithstanding diffraction effects. So they need to have a line of sight. So any vehicle that wants to communicate with quantum communications or try to have any sort of quantum position verification needs to have a line of sight with another vehicle or a line of sight with the infrastructure that it's passing.
So then we needed some kind of node in the middle, yes? We need a node if there is no line of sight, like a drone that can transfer the information. Is that right?
Yeah, so we've done prior work with using these payloads on drones, and they offer the flexibility of having a reconfigurable line of sight if you're trying to link up these mobile platforms or mobile robots. And really kind of our vision here is making quantum sensors and quantum communications ubiquitous with all things, with robots and with mobile platforms such as vehicles, drones, trains, cars, planes, satellites, etc.
And we also know that AFRL is interested in this technology. Can you maybe a little bit talk about the AFRL? So your project is sponsored by Air Force or by, is that Air Force, your project?
Yeah, so we have several Department of Defense sponsors that are interested in doing these links with drones as well as ground vehicles. And we look at this as doing QKD is obviously good for secure communication, but if you want to do entanglement distribution, which is also required for many distributed quantum sensors, you need to distribute entanglement through this channel. And a lot of the engineering challenges that you need to essentially have QKD from one car to another, you also need to solve if you're trying to distribute entanglement between these vehicles. And so we really look at it as developing this platform that is modular, that can go in multiple mobile platforms or robotics that can interface with quantum networks for both distributing entanglement, as well as doing sensing and secure communication.
Thank you, Dr. Clauser. Does it make sense?
Would seem if you already have a line of sight, there's you don't have you already guarantee that there's no eavesdropper just
So,
by looking.
yeah. So Andrew is showing us how to do vehicle-to-vehicle quantum key distribution, but Farbod is showing us how to ask difficult questions as he's driving to Portland.
So I'm trying to convince Dr. Clauser. If we convince him, that's it. That's it.
Yeah.
It's all right.
Okay. So we have one more question here for Andrew. Right.
Yeah, I mean, I was basically also going to ask, why are you doing this? But it
Okay.
seems like you answered that pretty thoroughly. So I guess I'll ask maybe a clarifying question real quick. So, I was thinking, why not use something like, Diffie-Hellman key exchange over something like radio, right? That seems like something much more straightforward, and doesn't have a lot of obvious issues. This does, but I guess my clarifying question is the idea that using quantum key exchange would essentially future-proof this, right? Is that kind of the idea?
Yeah, so I think if I go back to the very first slide, the U.S. Department of Transportation has the statistic that they're saying that 79% of all vehicle accidents in the U.S. could be avoided with the application of vehicle-to-vehicle communications. So this roadmap was done a while ago, literally 10 years ago. And in their roadmap, they envision using public key encryption over using radios. So car to car, car to infrastructure, et cetera. And while that's very good, in principle, as you pointed out, it's technically not future-proof. QKD is the only theoretical secure communication that is future-proof. So you can make that argument as to why you would want it to be QKD. But really, I think are all of the future nodes going to be having QKD links between all the other ones? Probably not. But I do think that they will have essentially quantum channels that are distributing entanglement to essentially extend these people as they're traveling to connect to the future global internet, which many people will believe will be a quantum version of that internet. So again, if you want to have access to the future version of the internet while you're in a car, you would need to have a QK or a quantum link. And it may not be distributing QKD necessarily, but you will need to distribute entanglement through those links. And so you would have to have a system that doesn't look like this, but it would have to have the same functionality of this, or probably a lot more functionality.
All right, thank you.
Yep.
Okay. One more question.
Awesome.
All right.
Hi, Andrew. Thanks. That was super interesting.
One more question.
Oh,
There's a question there. Sorry. Go ahead.
yeah, go ahead.
Oh, okay, cool. Well, first I want a couple of these, but two, when you're sending when Alice is sending the key or the actual key material to the other vehicle, don't you have to ultimately send the basis states that were chosen over a classical link? And if that's true, isn't that classical link itself insecure and not trustworthy?
Yeah, so that's a good question. So let's see, find this slide. Yeah, so I kind of briefly sketched the overview of how this QKD protocol works. And the idea is so after Alice transmits all of these QKD states through the channel, Bob receives them, he randomly selects these measurements. Let's say they only did this 5 times. So what Alice will do is say, okay, on the first one, I sent it in the DA basis on an RF or a public or an insecure channel. And then Bob will say, I announced it in the HV basis for that one. And because they disagree, they would discard that. And it turns out the way that the QKD protocol works is you do have to perform public announcements, but the announcements presume that any eavesdropper that would be there would immediately have access to all of those announcements. And if I tell you that I transmitted something in H or V, but I don't tell you which one it is, that doesn't help you out because you still have a 50% chance of getting it right or a 50% chance of getting it wrong. And so, yeah, so in order to implement this, you absolutely need an RF or another classical communication link between Alice and Bob. But it turns out the information that you need to put on that classical link is completely insecure, and it provides no information that an eavesdropper could use to acquire access to the secret key.
But you can't trust that communication in the first place, so that itself could be spoofed.
Okay, so you're referring to like authentication, meaning making sure that Alice is actually talking to Bob and not someone who's pretending to be Bob?
Yeah, just since you have you have this quantum communication channel, you have a classical channel, you're trying to establish trust between two vehicles. At the end of the day, you have to trust both of those communication to ultimately establish security, if I'm understanding it correctly.
Yeah, so that's really kind of a limitation with all QKD approaches, is that buried in the presumption is that the sender and the receiver are authenticated, meaning Alice is talking to this Bob and not someone else that's pretending to be Bob. So that assumption is required for all QKD links, not particular to this vehicle-to-vehicle QKD link.
Got it. Okay. Well, cool. Thanks for sharing.
Yeah.
One more question here. This is such an interesting topic.
Yeah, so Dr. Clauser, I think I don't have a question, but here is, I think, maybe a good circle back to maybe to be Dr. Andrew is an heretic. Heretic, right? We heard about heresy, right? So maybe he thinks that we may not agree with it, but who knows in 50 years. Thank you.
Yeah. Well, if there's another question, I'll defer to it. Yeah, I mean, I think
you have a solution looking for a problem.
Okay. All right. Any other question?
So, yes, we have. So Dr. Clauser said we have a solution and we're looking for liquids.
Looking for a problem.
Looking for the problem. So that's I think most of the time the case for research. But also I want to maybe argue that if we are like investing billions of dollars to develop quantum computers, and if we have access to at least hybrid system like quantum classical on like robots, like what we have computers on, like classical computers on vehicles and drones, then in that case, it's logical to have quantum communication if you have quantum computers rather than classical communication between two quantum computers. Don't you think so?
Yeah, I would agree with that assessment. And in a certain sense, I also agree that this was more or less a solution in search of a problem. I mean, we had these systems that demonstrated a successful QKD link from drones, and we just realized we could also put them in vehicles. Now, again, the question is, why would you want to do that? And I think the most basic fundamental level is that...
Stop!
Oh.
Yes. Sorry. Oops. Sorry. Okay. Sorry.
Was that a question?
We're about to hit a Tesla.
Should have had vehicle-to-vehicle communication.
Now it's on. Now it's on. I put it on.
Yeah, I mean, I guess I'll say, my closing comment is that more or less, we don't know what we're going to use quantum networks for. We are still developing this. This is still an active area of research as the community. And we don't know what new applications there will be for linking distant quantum computers together, what new quantum sensors can we achieve, as well as what sort of secure communication can be leveraged. And so I would say this is more building the fundamental resource of having quantum networks extend to mobile platforms. And QKD is one example of a quantum protocol that you can do, but you could have more or less have, instead of sending QKD, you could have distributed entanglement. And that's actually what we're working on doing next, is distributing entanglement. And once you distribute entanglement, there's a lot of other applications and potential use cases that could be done or could be leveraged. And so really this is, I guess I would argue, we're building the fundamental infrastructure of future wireless quantum networks. And what we do with them is kind of to be determined, and it's kind of up to the community to figure out what interesting ideas we have.
Okay, with that, let's.
Sorry.
Thank you, Lord Speaker, again.
Oh, okay, that's it. One last question, Marco.
One more
Sorry.
question. Oh,
One last question. So when you do QKD rather than single photon, do you send one of the signal or the idler to Alice herself, and the other one to Bob, or do you generate it from somewhere else and send it to Alice and Bob? So if it is generated from, do you generate it from Alice?
Yeah, so what we want to do next is essentially put an entanglement source on Alice, and so she could produce one photon, keep it locally, and then transmit the other one to Bob. And you could do entanglement-based QKD, but there's other applications that you can do, such as like quantum teleportation, which would be interesting as well.
So the source and one detector is on Alice and the other detector is on Bob. Is that right?
Yeah, that's what we're planning to do next. But as you point out, Farbad, Alice could receive an entangled pair from somewhere else, as well as Bob could receive the other half of the entanglement as well.
Okay, so both cases are possible.
Yeah, that's correct.
Okay, thank you.
okay.
Thank you very much.
Are we done? Thank you again. Oh, before everybody leaves, so if anybody has any suggestion for the next workshop or any other pressing questions, please email us, or both myself. We'll try to answer in short time. Thank you.
Thank you.
Awesome. Thanks.